This program is brought to you by Stanford University. Please visit us at stanford.edu.
Okay, so what lecture is this? Lecture number? 4. Okay, so what did you learn in the first 3 lectures?
How to convert feet into meters.
Feet into meters. What?
Acids.
Yeah.
Dropping acid?
No.
What?
Well,
What? That's flow sheets. What about flow sheets? What are they good for?
mapping out.
Modeling things, mapping out, bookkeeping, keeping track of stuff. So you have these little boxes in our flow sheets, and material or energy goes in, and material or energy is going to come out. Sometimes energy might be produced because what happens in a reactor, for instance? Why would energy be produced? What would happen? Something's either broken or put together. What? Bonds. Chemical bonds. Okay. And we might enhance the speed of reaction by doing what in the reactor? Having what in there? A catalyst. And you also did learn hopefully about units, why they're important. You don't want to make mistakes in unit conversions. One of the good things we'll be talking about as we go through the class is you'll be asked throughout life to work lots of problems. And not only do you want to be sure that if you're trying to compute a velocity, it's not in, what did I say, candelas per hour. That's not a velocity unit. So something must have gone wrong. If you do get a velocity unit out, and let's say you're computing the velocity of syrup coming out of a cup, and it turns out to be in excess of the speed of sound, 800 miles an hour. Now you take your engineering sort of intuition and say, that doesn't seem right. Faster than the speed of sound. If you do think that's okay, what do you major in? Poli-sci, sociology, or maybe even psychiatry. But you might rethink engineering. So I'm also going to try to get to know you folks by name. And that's hard for someone my age. So I have 2 ways I can do that. I can just say, I can put the question out and then point to you and say, what's your name? Answer the question. People really got unhappy when I do that. So when you do answer a question, I might ask you your name, and I'll just try to make faces. I know a whole bunch here in the peanut gallery up front, because I've had several of you in class before. The peanut gallery has shrunk. What's going on up there, Sasha?
No idea.
Huh? No idea? Who are we down to? Who's in the peanut gallery? Let's see if you know him. Sasha? Who else? Sashank? What? Come on. David. Got it? And where's Max? Here's Max. Okay. Any announcements from the peanut gallery or Max?
So the prom session on Friday will either be held in here or the gazebo, so that's nothing new. We have a room.
Okay, we have a room for Friday. We'll let you know during the lecture where it's going to be, the problem session on Friday. When is the problem set due?
Today.
Today. So I see some of you working on it. That's good. We have a field trip when? And what do you bring? Okay. That's good. What is this? You got it. This is what Perry's looked like. 2nd edition. Published in what year? 1910. 1910, okay. You got the right century. 2nd edition. Look at this little thing. McGraw-Hill Book Company, 1941. Even before I was born. Not far, but even before I was born. That's what it looked like. Now you can see they had a design problem. It was either just going to keep getting like this, it's the same size, or they went, and here we have, if you look inside here. So Theo, what does that say right there?
I don't know how to read it.
Come on, Theo.
Berkeley, California.
Yeah.
1964.
So this is Channing Robertson, 1921 Francisco Street, apartment 6C, Berkeley, 9, California. This is even predates zip codes, because Berkeley 9 was sort of, the equivalent of a zip code. And fall 1964.
Is that Mrs. Noyes' apartment?
This is Mrs. Noyes' apartment. Have I told the Mrs. Noyes story?
We know it.
Oh, you know it. All right.
You have to tell them.
Well, I was in Berkeley. We moved into a boarding house. Remember told you all these friends of mine from high school? And there were 7 of us. And our parents drove us up and dumped us in front of this boarding house they had found. Mrs. Noyes, N-O-Y-E-S, we call her Mrs. Noyes, was running it. Unfortunately, she was an invalid and couldn't go upstairs. It was 3 stories high. So she hung around on the lower floor in her wheelchair, and we took over the upper 3 floors and proceeded to dismantle and destroy them. And she'd yell at us, "What are we doing? What are we doing?" There'd be water coming down the stairs in a river. We're not doing anything. We're taking a shower. Mrs. Noyes says, "No problem." It was a fun place. It was on Hay Street, right off Telegraph Avenue. And then the one thing my parents did for me is they did provide me with my rent. It was $35 a month. Furnished, if you could call it furnishings, but furnished. And came Christmas time, my mother said, none of the rent checks are being cashed. What are you doing with them? And I said, well, we put them under Mrs. Noyes' door. And then we came home from school one day, and the coroner's wagon was out in front, and there was tape up, and we looked around, and it turned out the reason the checks weren't being cashed is Mrs. Noyes had passed away several months earlier. And she's still sitting in her chair watching this the TV had burned down to about this little light, it was kind of closing in. It didn't matter to her. She's just sitting there, been sitting there for quite a while. So I looked in there and I saw this. It was like the last scene in that Hitchcock movie, The Birds, was it? Yeah. And I saw my checks on the floor. I gathered them all up, ran, and poor Mrs. Noyes, but she didn't have any use for them. And so then the health department shuts the place down. And they said, well, look at all the mold that's growing in the place since she died. Well, that happens to be where we were living, upstairs. The mold was from all the water fights. And so they said, you guys are going to have to get out of here. So we took the doors off our room, used them like a stretcher, and we went up to the housing office and said, you have to find us a place to live. Because look, this is the door from our boarding house, and the woman's dead for months. And they said, okay, well, we've had a lot of people flunk out the first semester, so we'll put you in the holes where these people have flunked out. And sure enough, I ended up getting put into Deutsch Hall, one of the high-rises up there, with a guy named Bud Holmesy from Fresno. And his roommate actually hadn't flunked out. He was a predator. And he sat on the balcony with a blanket over his head with a telescope looking at the women's dorm, which was right across from us, scanning, like a raster scan. He would do like this, and then he'd go up and do this all day long until he flunked out. And so this guy Holmesy, I never knew who he was. I was just in there. You know how it is. You meet your roommate. And he says, when do you sleep? I thought, that's kind of a weird question. When do I sleep? I said, I sleep at night. He says, well, I sleep during the day. So let's get rid of one of the beds. I'll use it during the day, you use it at night. And I turn around and he's hawking the mattress out the window. Which wasn't a problem, except we were on the 8th floor. And this thing went right through a skylight on the eating commons. And then he hawked out the box springs and the rest of it. And Fat Mama, who was the woman who was supposed to take care of us, she lived on the 2nd floor. She was too large to go in the elevator, so she couldn't come up to see us. She says, someone threw a bed out. What? Bed? We don't know anything about that. So Holmesy and I went through Berkeley together, and we both went off to graduate school. And sure enough, Stanford hired us onto the faculty the same year. Had no idea we knew each other, much less we're roommates. Talk about incest. And he stayed on the faculty for, 25 years before he decided to go down to Santa Barbara and be in the chemie department down there, i.e. be on the beach. And that's where he is. If you look outside Stauffer 3, you see a tree. It says Bud's Tree. So it's this thing I had planted in his honor when he left Stanford. And it was really cool because we were having this outdoor reception. He didn't know what was going on. I had one of the tree guys on campus, a good friend of mine, had him pick this tree up in a big crane and bring it over and stick it in the hole during the reception. It was a very cool thing. So you see Bud's Tree. It's the second Bud's Tree. The first Bud's Tree died. But, and so this is the second Bud's Tree. This is Perry's Chemical Engineer's Handbook. This is the 7th edition now. And this is what you all want to buy. And it says, you are the recipient of the Donald Othmore Sophomore Academic Excellence Award. Turns out I nominated a sophomore for this, and the sophomore got it and then flunked out. And so I took the book back, and so now I have it. I mean, what a loser you are. I said, flunk out, you can give me the book back. So, and what year was this? This is what was it? 69. So there might even be a newer edition out, but this is the one I have on my shelf. So I'm going to set it here so you can admire it throughout the lecture. And that's a little one, so you could admire history, and you could admire Mrs. Noyes. All right, we're 15 minutes into this. We've done absolutely nothing. So we're going to talk about, we talked about what you've learned. And so I've got to do something so when I ask you this next time, we did something in this lecture. So we're going to talk about process design. So what I'm going to do is show you quickly how you can actually put together a flow sheet to design a plant. And it's really kind of cool. This is a plant that makes ammonia. So you want to make ammonia. Why do you want to make ammonia? Smelling salts? What? Fertilizer? Fertilizer. Great. You're right. Fertilizer. Now, do you go down to the garden shop and buy a big canister of ammonia and then spray it out on your yard? Huh? Have you tried that? No, you don't. You put something on your lawn. Usually it's in particles, right? Put it out on your lawn, and then what do you do to the lawn to get the particles to go in and see the roots of the plants? You water it. Dissolves the particles. So ammonia is really not the fertilizer. But the fertilizer typically is a compound called urea. And urea looks like this. So you see, the reason you use urea is because it only takes one carbon atom. You can lock up 2 atoms of nitrogen on urea. So it's a good way to store the nitrogen. This is like a salt. It's a solid. It can be granular. You can put it out on your lawn. So if you start with ammonia, and you want to end up with urea, which is CONH2, what would I have to do to make that compound, urea? Ammonia plus what, do you think? Something with carbon in it, maybe? Huh? What's a real cheap source of carbon is CO2. Now, does that balance? What do I need to do? Well, I know I have 2 nitrogens over here, right? So I better put 2 of these in. Now I've got 6 hydrogens. I've got 4 here. So I must have some hydrogen left over. And how about oxygen? I've got 2 here, 1 here. Whoa. There you go. Take carbon dioxide, put it in a reactor with ammonia, you make urea, and you get water. And so what do you do when you water the lawn? You turn the reaction around. You put water on the urea, and you get the ammonia back out, and CO2. So ammonia is the first step to fertilizer. See, that's not scary chemistry, is it? You're looking at me again like I'm out of my mind. Now stop that. Huh? Roughly correct, Theo. Thank you. So there we go, making some ammonia so we can make urea. So let's draw the plant. Well, here's the plant. Reactor, nitrogen and hydrogen in, you make ammonia. Well, do you think there's a little bit more to the plant to that? Where do the nitrogen come from? Air. Where is the hydrogen going to come from? And I've had people say balloons and blimps. That's not where it comes from. They're no longer in the major either. Well, electrolysis of water, that'd be one way of doing it. Maybe burning some molecule that will generate hydrogen, that has hydrogen in it. And you think of something you use in your house that you burn. Your little sister's dolls. I mean, what do you burn? Like methane, right, in your stove. Might be able to get some hydrogen out of that. So let's see what this plant really starts to look like. And here's some clues for you. Here's some boiling points at 1 atmosphere. Here's ammonia, minus 33, hydrogen, minus 253 degrees centigrade, and nitrogen, minus 196. So if I take this mixture of ammonia, hydrogen, and nitrogen and cool it below minus 254 degrees, they are all in what phase? Liquid. Good. All right. If I start heating it up and I finally get to minus 253, what happens? 254, hydrogen starts coming off. It boils off, right? You're above its boiling point. And then the next one would be nitrogen, and then you'd be left with ammonia. So we might be able to make some use in separating these things from one another on the basis of their boiling points. So let's look at our flow sheet again and say, well, somewhere we have a source of nitrogen and hydrogen. It goes into our reactor. And this reactor is magically going to make ammonia, but no reaction is ever complete. We'll always have some nitrogen and hydrogen left over. And so we put it into a condenser, and if the condenser's below at minus 35 degrees centigrade, what phase is the ammonia? It liquid, so it comes out, the gases go overhead, and can be combined here with the nitrogen and hydrogen coming in. So we've built a little bit of our plant just knowing that we won't have a complete reaction always to ammonia. Now, we do need the nitrogen and hydrogen. And somebody said, well, let's take, what do you think this is coming in here? Air. So if we have air coming in and we put it through a condenser at minus 190 degrees C, why is the oxygen coming out here? Because it's a what? A liquid. So we can separate a liquid from a gas pretty easily. So there's our nitrogen source. Our hydrogen's coming in. We don't know from where yet. But you see we've backed up here to the left a little bit. We have now nitrogen and hydrogen. Here's this piece of it, the reactor, the condenser to get out our ammonia. Recycling, and this is called a recycle line. When you take something from one unit and put it upstream in the process, that's called a recycle line. So how can we get hydrogen? And somebody said from water. Now, if you take water, a gas, let's say steam, and you put a bunch of energy into it, you can actually bust the bonds that hold the hydrogens to the oxygen. And you can make hydrogen and you can make oxygen. But it does take 242 kilojoules per mole of water. It takes a lot of energy to do that. So then the next question is where are we going to get that energy? We're going to have to get that energy. And one way we could do it, somebody said electricity. That's true. But where do you get the electricity? Does it just come out of the sky? No, you get it from coal, or you get it from oil, or you get it from natural gas, or you can get it from solar voltaics or wind or what have you. So let's see where we're going to get that energy. And one way you can get that energy too is from chemical reactions. All right, so let's look at this chemical reaction. where we're taking methane, adding oxygen to it. So what's this called? When you take methane and add oxygen to it and stick a match under it. It's combustion, right? So this is just combustion. It makes CO2 and water. And 803 kilojoules per mole of methane burned. So if you take this chemical equation and you take the one that we had on the previous slide of taking the steam plus some energy, breaks this up into hydrogen and oxygen, you can see if I multiply this by 3.3, so that, because 3.3 times 242 is 803, and add these two equations together, I get that if I take methane, burn it with 0.35 moles of oxygen and 1.3 moles of water, I can produce a mole of carbon dioxide, 3.3 moles of hydrogen, and it's net energy neutral. So I'm basically taking the energy given off in this combustion reaction to drive this reaction from left to right. So I can imagine having a reactor or a burner where I feed in methane, oxygen, and steam, and I'll get out CO2, hydrogen, why am I getting some methane out here? It just doesn't all get used up, all right? Unfortunately, we can't get reactions to go 100%. I'm going to have some water, steam that might come through, and some O2 that might come through as well from my little reactor burner. But nonetheless, this is a way I can produce some hydrogen using the energy from the combustion of natural gas. So here we have our little burner. Well, what I'm really interested, of course, is getting hydrogen out of here. And you can see if I put this mixture through another condenser, I can knock out the water and the CO2 based on boiling points, and have the methane and the hydrogen, the unburned methane and the hydrogen I've made, go over the top. So let's now put this together in an even bigger flow sheet. Now you can start to see how that little box I drew at first, which was just nitrogen and hydrogen going into something called a reactor and ammonia coming out, it's getting a little more complicated. So let's see where we are. Here we have, what's this going into the condenser? Air. Here comes the oxygen. But you see, we use the oxygen to feed the combustion reaction with the methane and the steam coming in the reactor burner that we just talked about. Here's the products coming out. We knock out the water and the CO2. We take the methane that's unburned and the hydrogen, and there's our hydrogen stream coming in. Here's our nitrogen stream coming in from the air. That goes into the reactor to make the ammonia, the hydrogen, the nitrogen, and you can see this is not in your notes because I forgot to put it there, but we have some methane coming in, right? And so we're carrying the methane through. We go into the condenser, we knock out the ammonia, comes out as a liquid. The nitrogen, the hydrogen, and the methane go overhead, get recycled back, and get put through the process again. Now you'll notice we've got a couple streams here. Purge streams. There's nitrogen coming out of this one, and there's what's ever in this stream, which would be nitrogen, hydrogen, and methane coming out of this one. Why do we do that? What would happen if we didn't have those purge streams?
Pressure would go up.
Okay, the pressure would go up. What's that equivalent to saying?
Change the fluid.
Exactly. We have to balance this, right? This all has to be balanced because we have nitrogen coming in, we have hydrogen coming in with the water that we're splitting that. We're making ammonia coming out, but we have to balance it so that all the nitrogen and oxygen, all the carbon, all the oxygen here coming in has to match what leaves. Well, it won't match what leaves here and here. There's going to be a buildup of excess of unburned methane, so we've got to bleed it off, and some unused nitrogen. And that just has to do with what the stoichiometric ratio is of nitrogen and oxygen in air, which is 20 to 80, roughly, 21 to 79 or something like that. So unfortunately, air didn't come in exactly the right ratio in order to make this work, so we have to balance it by bleeding it off so that we don't accumulate nitrogen or methane in our process. And then what we can do is we can have this run at steady state. We can have air coming in, we can have steam and methane coming in, match it with the oxygen we get from the air, and this whole thing will work and our plant is complete. At least conceptually it's complete. And then, of course, what we have to do is to start attaching numbers to this. And that's what you'll be doing in the next couple of weeks. So how many pounds of air are coming in, or how many pounds of nitrogen and oxygen, or kilograms of nitrogen and oxygen? How many kilograms of methane and steam are going to be needed in order to make this work? And then how much are we going to have to vent, and what are we going to do with that? And this is the product that we're making and selling.
Could you not use the methane and recycle it? Is that from the first stream?
So we have some methane being recycled right here.
But that's not reacting. The methane there is.
That's right, and the methane is not reacting. So, okay, the point is, could we take some of this and bring it down and use it to feed in here? Yeah, we could. Good point. You could feed that back into here, but you're also going to be bringing some nitrogen and hydrogen, aren't you? So is this a good idea? Oh, geez, what do I have coming in here? Oxygen. What happens when I take oxygen and hydrogen and stick it in a burner? But you have no plant. You see, your plant spread thinly over about 4 square miles. So that seemed to be a good idea until we sort of noticed this. But maybe what we could do is knock the hydrogen out of this stream before we fed it back. Now, that's going to cost you some money, because you're probably going to have a condenser. And so you have to weigh that against just blowing this out into the atmosphere. And that's an engineering decision. It's an economic decision that you would make. Because every one of these little boxes, think about it, costs you money. And the one thing you're going to learn in this class is you're not going to turn gold into lead. See, that's what a lot of people do. They make a plant, they turn it on, and then they look at the cash flow, and they're turning gold into lead. Huh, I'm not making any money, but I've got a really nice looking plant here. That's when you hook this stream up to here and walk away. And then you call your insurance company. You say, well, I don't know what happened here. I had this chemical engineer from Cal come in here. And so, all right, so that's how you begin to put flow sheets together. And now we have to figure out, how do we put numbers on the flow sheets? So that we can track the masses that are going through of the various material. You do that using conservation principles. We conserve mass. We're not in the process of building nuclear reactors necessarily, where mass isn't conserved because it's exchanging between mass and energy. We'll conserve energy. We'll conserve linear and angular momentum. This is a course you'll take later in fluid mechanics. We will do mass and energy in this class. The reason we do that is because mass and energy are scalars, like temperature or grams. Mass is a scalar. It just has an absolute number associated with it. When you get into fluid mechanics, really what you're dealing with momentum and so forth is m times v. V is a vector. Velocities have direction and magnitude. It gets a little bit more complex. You need to grow up a little more before we can do that for you. And so you'll suffer through that in your junior year, or probability charge and what have you. So let's talk about conservation of mass. So here's a little process. And this little process, this is just a boiler. And we're going to pretend that this is a desalination unit. So we have seawater coming in. We heat the seawater up. The vapor that comes off is water. And how much salt does the vapor contain? Not very much, hopefully, right? Because you're not going to be boiling the salt. This is not a molten thing. So, and you take this water vapor off and you condense it and you can make fresh water. And then coming out here at the bottom, is it saltier water or less salty water? Saltier. It's saltier because you're concentrating the salt, right? And so the question is if I have so much seawater coming in, how much fresh water do I get out? And how much salt water do I get out? So the first thing you always do when you do a mass balance. And this could be any one of the little boxes in that previous flow sheet I just did for you. You have to label the streams. 1, 2, 3. And this can get complicated. I can remember in the equivalent class I had back in 1962, I had it from a guy named Ed Grins. He was an old Marine sergeant turned chemical engineer. And he didn't have a nice little peanut gallery and a max like we do. He had this goon squad. And he'd walk in, and the goon squad would follow him. They all had shades on. They all had crew cuts. And they all had hair coming out of their shirts. And he said, and it was always gentlemen, because in that time there were very few women in chemical engineering that we knew of. And he would come in and he'd say, gentlemen, these are your TAs. Well, these are not people you even wanted to socialize with, much less talk to, or go to office hours with a closed door. I mean, you don't know what they were going to do to you. And he says, and gentlemen, I want you to look to your left. Now look to your right. Those people will be gone at the end of this class. Now that's kind of the motivation that you got. Right away, everyone's going to be exterminated by either him or the goon squad. So the final we got in that class was a small, looked like a book when we got it. But we found out it was one of these fold-out things. You just folded it out and folded it out. It turned out to be a sheet of paper that was like 7 by 7 feet. And it was an entire chemical plant. When I got through just labeling the streams, I was up to 430. And we were supposed to do the mass balance on this plant with slide rules in an hour and a half. But it was a complete joke because there was an element that was coming in the plant and going out the other end that didn't suffer any chemical reaction or wasn't added or subtracted to, and that's all you had to figure out. It's called a diluent. And if you had figured it out, you got the answer. And if you didn't figure it out, you went into therapy. And that was how he flunked 85% of the people in the class. They're all madly working. And I figured, I can't work this, but look, there's something coming in, titanium, and it doesn't seem to be reacting, so the amount of titanium in must equal the amount of titanium out. And I wrote that down, and I walked out, put that in my blue book. 2 lines, 100. You stick with Chambo, and I'll get you through this, all right? Life is simple, right? If life becomes complicated, if you're working any of my problems and they get complicated, you're screwed. Stop it. Back off. It's got to be simple, all right? Because life is simple. No use to making complicated. This is very simple. Little boiler. That's a heater, by the way, right there. I did that on PowerPoint. And so now FT is the total mass in stream 1. FT2 is the total mass in stream 2. It could be, and we do this in rates, so it'd be like kilograms per hour or tons per minute. And if there are 2 components, in this problem, our components might be water and salt. Now, why you might say, don't I treat salt as sodium and chloride? I could. But if I'm not separating the sodium and chloride anywhere, why bother? Why not just put them together and track them? Because they'll always be together. So this FA could be the amount of water in stream 1, FA2, the amount of water in stream 2, FA3, the amount of water in stream 3, and FB could be the amount of salt in stream 1, salt in stream 2, and salt in stream 3. And if I add FA3 to FB3, what should I get? If I add those 2 together, I should get FT3, the total, okay? So you can have the total mass, or you can have what are called the individual items of mass: water, salt, sodium, chloride, and so forth. But the first thing to do is label everything, get all your subscripts right, because basically you're going to end up doing a bunch of algebra. And it's much easier doing the algebra with symbols than with numbers. You plug all the numbers in at the end. So let's do a mass conservation, a mass balance, if you will, around that little unit on the previous page. So the mass at time t, if you subtract that from the mass at t plus delta t. So we've got this little, think of this little pot. We have a stream flowing into it, and we have 2 streams coming out of it. All right? So all this says is that if I look at the mass that's inside my little pot at T plus delta T, and I subtract what it was at T, it must be equal to what? The amount of mass that went in, remember that's the total amount of mass going into stream 1, minus the sum of the masses leaving. Now this is, remember, pounds per hour, or tons per day, times delta T. Now if I take the limit of this, remember calculus? If I take the limit of this, I get that the rate of change of mass in my little tank is simply equal to the amount of mass going into the tank minus the amount of mass leaving the tank. That's pretty simple. You'd actually expect that to be the case. If I'm putting more mass into the tank than I'm taking out in those other 2 streams, what's going to happen to the mass inside the tank? It's going to increase. The liquid level is going to rise. If, on the other hand, I'm taking more out than I'm putting in, what's the sign of dm dt? It's negative. Now, we can put this into words. The rate of accumulation is equal to the rate of input minus the rate of output. Now, this may seem pretty obvious, but this is really very, very key. Because all it's saying is that if the rate of input into my system exceeds the rate of output, I'm going to accumulate. And if the rate of input's less, then this will be a negative number. Rate of accumulation will be negative, and I'll be depleting mass. And at steady state, where things aren't changing with time, so the liquid level is not rising or changing with time, the mass isn't increasing or decreasing with time, the rate of accumulation has to be what? What's dm dt if nothing's changing with time? It's 0. So the rate of input equals the rate of output. And that's what we mean by steady state. A lot of people get steady state mixed up with the concept of equilibrium. They're not the same. When you're at equilibrium, what are you? When any one of you reaches equilibrium, what are you? You're friggin' dead. All right? You're at steady state right now. See, it's the difference between life and death that you understand this concept. All right? Most of you are at steady state. Some of you are in slow brain death, you know, but you're not in rapid decline. You're not dead yet. All right, I got a piece of meat here between my teeth. Let me drink it. Oh, thank you. Dessert. All right, here we go. Now, we just did what was called a total mass balance. A total mass balance on our process is simply everything that goes in must equal everything that comes out. But you can do component balances. You can say the amount of, let's say this is water going into the process, must equal the amount of water that's leaving in the 2 streams. The amount of salt going into the process must equal the amount of salt in the 2 streams. So you can have component mass balances. And if I add these 2 equations together, as I've done here, do you see that this just gives me what's called the overall mass balance? Because FA1 and FB1 is simply the total mass in stream 1, which is FT1. So I can generate how many equations every time I do a balance around a unit when I've got 2 components. How many equations can I write? 2 components, and I want to write mass balances. 3. A total plus 1 for each component. So if I had 3 components, I could write how many equations? 4. How many of those equations are independent? If n is the total number of equations, any example I give you, how many are independent of each other? N minus 1. Why? Because I can always add these 2 together to get this one. If I have this one and one of these, I can always get the third one. So there's only, in this example, there's only 2 independent equations. So one of the things you're going to have to watch out for is sometimes, and I'll do this for you ad nauseum, is you write down all the equations you can think of. But you know now that you've just heard this, that some of those are not going to be independent. They'll be dependent. But that's okay. If you write down too many equations, you'll get things like 2 equals 2. right? You know, you'll be grinding away and you get these tautologies. Well, that's okay. It just means that was one of the dependent equations. The problem you'll run into is if you don't write down enough equations. Because if you don't write down enough equations, then you don't have enough independent equations to solve the problem, and you get a new major, okay? Because you can't solve the problem. You go away frustrated. So let's take this desalinator and let's actually work it. Here's seawater. Seawater is 96.5% water and 3.5% salt. Okay, so that's what you get in the ocean. Potable water, water you can drink, that you can stomach, except if you live in New York, right, Theo? It's 99.95% water and less than 0.05% salt. So this now gives us a design limit for our desalinator. We're going to have to drive the salt concentration down to 0.05% or less. Now, the problem that you're given is analyze a desalinator that produces a pure product pure water, and a waste stream that's 27% brine. Now, what does that mean? A brine stream that's 27% is 27% by weight salt. And therefore, it's 73% by weight what? Water. All right? So that's the problem. And you've given your input to the process is 100 kilograms per minute of seawater. We always take a basis. Does that mean that I'm limited to 100 kilograms per minute of seawater? That's all there is in the ocean that will allow me to run this? No. You just pick a basis, because once you work it for 100 kilograms per minute and get all your answers, if in fact your feed is twice that, you just multiply everything by 2. So you just pick a basis that makes sense. 100's a nice number to start working with. If you want, you can pick a basis of 43.789 times pi grams per minute going into your plant if you want. Right? Not if you take this class. Maybe if you were at some other university whose colors are blue and gold, you might do that, but not here. Not, oh, the women's game. Oh man, that just reminded me. That was too bad. That was a great team. All right. So the first thing you do is you draw a flow sheet. Now this flow sheet's really simple. It only has one unit to it, our desalinator. We have our streams 1, 2, and 3. One coming in, the seawater, the water stream coming out, and our 27% brine stream. So you write down everything you know, and then you put a little dotted box. And you know why you put the little dotted box? Because a little dotted box cuts these streams. You see how it cuts it here, cuts it here, cuts it here? So that when you make a mass balance, you know to be sure that you need to inventory any stream that cuts your little control volume. Because mass is either crossing that boundary or leaving that boundary. So that's a good way, because you can see on that big plant we did, I could draw lots of little dotted boxes. I could draw them around 2 of the units, 3 of the units, the whole plant, and you will be doing that in order to achieve doing the full mass balance for a complicated plant. So then you define your variables. Well, we've done that. Ft of I is the total mass flow rate in stream I, 1, 2, or 3. Fw, why do I write Fw? Just to remind you, it's water. And Fs for salt. Now, if you don't like it, you could call it Fn for NaCl, or Fl for NaCl, or Fz for salt, if that's the way you think it's spelled. However you want to do it. But just remember, you need to know what it is. So that's step 2, is define all your variables after you draw the process and draw your little dotted box. Step 3 is apply an overall balance. So Ft1 is the amount of total mass going in across stream 1 equals what comes out across these 2 and 3. We know 100 is the amount in is equal to F2 plus Ft3. Now we can do component balances. Do we need to do both component balances? Salt and water to get a solution to this?
No.
If we did, why don't you want to do that?
It's dependent.
Because one of those is dependent. You could pick either one. I pick salt. You could pick water. Doesn't matter. So here we have XS1 times FT1. So what's this XS? XS is the mass fraction of salt in stream 1. So it's that fraction of stream 1's mass that is salt must equal the mass fraction of salt in stream 2 times the total mass of stream 2 plus the mass fraction of salt in stream 3 times the total mass of stream 3. So what is the mass fraction of salt in seawater? It's 3.5%. So 0.035 times 100 equals, well, remember this stream was 0.27, 27% salt times FT2 plus, we're assuming no perceptible salt in our fresh water. You could, but we're not going to in this example. So right away I can solve for FT2. So FT2, this stream is 13 kilograms per minute. So this is 100 and this is 13. So right away I'm beginning to solve the mass balance. I'm beginning to find out what the magnitude of these streams is. Now, step 5. Let's solve for the water production rate, which is FT3. Well, I can do that by using the overall mass balance, which is FT3 is equal to FT1 minus FT2. 100 minus 13, so it's 87. See, it all has to add up. You have 100 going in, you got 13 coming out the bottom, you better have 87 going out the other end. Now you can do a check. Never be happy. This is where you use the dependent equations. If I now plug my answers back into the one equation I didn't use, I should get an identity if my answer is right, shouldn't I? It should solve that equation. So here's the water component equation. Mass fraction of water in stream 1 times the mass of stream 1 equals the mass fraction of water in stream 2 times the mass or mass flow rate of stream 2 plus the mass fraction of water in stream 3 times the flow rate of stream 3. So what is 0.965? Mass fraction of water in the incoming stream, that's the ocean, times 100 kilograms per minute equals, now why do I have 0.73 here?
Minus 27%.
Okay, it's 100% minus 27%, so it's 73% water. I figured out that it's 13 kilograms per minute, plus I've said XW3 is equal to what in this example? 1. I said there's no salt in stream 3, so it's just 1 times 87, which I solve for. And you can see I get 96.5 equals 96.5. So it must mean my math was correct, because I solved my dependent equation as an identity. All right, now you might say, wow, Chem E is cool, it's easy. You see, that kind of problem I could have given you, and you know what you would have done? You would have intuited your way through it. You would have sort of just figured it out. But you wouldn't have had the discipline of drawing the box, drawing the control volume, writing down your variables, writing down your 3 equations, solving 2, and checking with the 3rd. That's the discipline you need to get from today's lecture. Because when I give you a really hairy Mongo flow diagram, do this. If you think you can intuit it, ask your roommate to do it. Tell him. The prof said this is intuitive and that anybody who's been accepted to Stanford can solve this. Give it to them. Watch them in agony as they try to figure it out. And you're sitting there, you'll draw your flow sheet, they'll watch you draw the little dotted boxes, you write all your variables down, you write the equations, you solve them. You go have a mint julep while they go into therapy. So you really need to follow this process because it can get you through very, very complicated mass balances, as we'll see. So what we're going to do now is we're going to design something. So I believe in, and just let's put this to work. So starting the next lecture, we're going to design an apheresis machine. And then we're going to actually go see the apheresis machine on Monday afternoon. So you're going to be able to take these simple concepts and actually do something useful with them. If you don't know what apheresis is, who can spell it? A-P-H. I had someone last year, I tried to Google this, AFE, I got some really strange websites, some really bad things you told me to go see. I don't know what you get when you write that down. But anyway, it's APHER, AFER, something S's. And if you want to, you can read some of the stuff and get an idea of what apheresis is all about, because I'll ask you before we get started to see if anyone actually did that. Has something to do with taking platelets out of blood. And you'll help yourself if you actually just spend 15 to 20 minutes looking at that and rethinking about what's in blood and what blood is, because that's the fluid we're going to be working with on, Friday.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.